Thanks. Okay, so I have a little bit of a difficult task today. I said I was going to say something about stability conditions in the Braid group. I think that was even the title of the workshop. So today I have to do that. So let me remind you approximately where we left off last time. So we have the basic thing we're studying is we have a triangulated category. This is the homotopy category of bounded complexes of graded projective modules over the zigzag algebra. It's a triangulated category, and it has an action of, has a linear action of the Braid group on it. And where we ended last time is, so now this is, so now we want to start doing some sort of, we want to start using homological algebra. I mean, the language of triangulated categories and their structure is the language of homological algebra. We want to start using some homological algebra to say something about the group. And I gave you a small example of that last time. So a small example of that said, well, look, one piece of structure that homological algebra gives you on this triangulated category is, well, there's a natural T structure on this category, which informally is a way of thinking of the category as a non-negative part and a non-positive part. So I drew this picture last time, and I want to remind you approximately what it means. So there were some axes here. There was this one axis, which was like internal grading. Another axis was homological degree. And there's a very important subcategory of this category, which is the horizontal line here, the linear complexes. So the linear complexes, those were ones where in the minimal, those were complexes where in the minimal complex, the internal grading shift and the homological degree match. So there were these linear complexes. And then, up here there's the stuff where the internal grading shift is, say, greater than the homological degree, and this is the internal grading shift is less than the homological degree, or maybe it was minus the homological degree, but okay, anyway, that's a matter of convention. So there was this part here, this subcategory here, and this subcategory here, and the important thing about this decomposition, one important thing about this decomposition is that there are no, if you have an object up here, there are no morphisms to objects down here. So the only morphisms go in this direction. So the possible morphisms go in this direction. This is an example of a T structure, which I'll give you the definition of in a moment. But this particular T structure was important because it was somehow nicely compatible with the action of the positive and negative braid monoids. The negative braid monoid has the tendency to move you in this direction. In particular, it preserves this part of the T structure. And the positive braid monoid has the tendency to move you in this direction. In particular, it preserves this part of the T structure. Okay, so now the way you if you don't know about these things, the thing you should keep in mind is, so a T structure, which I'll define more formally in a moment, allows you to filter complexes so that the subquotients are linear. Yes?
In the story with Schrödinger side, and it has a geometric interpretation. You have sheaves of G, BD equivariant sheaves of G. Then this T structure is a perverse structure.
Yeah. That's right. I mean, another algebraic way of saying this is, at least when the original graph was not type ADE, so an affine and other type, then the zigzag algebra is Cazul, and its Cazul dual is the pre-projective algebra. And if you look at the derived category of modules over the pre-projective algebra, that has an obvious T structure whose heart is just the module category. If you transport that heart by Cazul duality, this is the T structure you get. Okay, so T structure allows you to filter complexes such that the subquotients are linear complexes. And before giving you the general definition, I just want to kind of let you see it in pictures. So for for most of today, just to hopefully make things a little simpler to understand, I'm just suppressing internal gradings. I'm not drawing internal gradings everywhere. In lieu of drawing internal gradings and drawing homological degrees, I'm kind of drawing the differentials in a chain complex either horizontally or vertically to tell you where it moves in this T structure. So this is a chain complex. I mean, I haven't told you exactly what the differential is here, but it doesn't really matter for this. So this is a chain complex. All this white stuff is a chain complex. And you can see that this chain complex has a filtration by has a sort of something kind of like a Jordan-Holder filtration, filtration whose subquotients are linear complexes. So you can, for instance, or shifts of linear complexes. So for instance, here's the whole complex. This term by itself is a subcomplex. And and then the rest is this. And this term, of course, is a shift of a linear complex. It's in the shift by 2 of linear complexes. And then if you looked at this and repeated, you could look at this part here, which is a subcomplex of what's left, and so on. So so this original complex gets sliced into these pieces, and each of these pieces is a shift of a linear complex, and moreover, as you go along from the first subquotient to the second, the shifts decrease. So that's what a T structure is. And in this example, you can kind of picture it. So let me say that a little bit more formally. Oh, by the way, I'm going to have there's a running assumption here, which I won't say much about assumption. So some things that I'll say today hold in much greater generality than for the triangulated category we're studying. But for us, all of the triangulated and abelian categories, so let's say all of the abelian categories have finitely many simple objects. And all Grothendieck groups are finite rank. So that for some of the definitions in Bridgeland stability or some of the theorems, you need to either make this assumption or you need to say something. There are many situations, there are many triangulated categories one cares about where these assumptions don't hold, but the kind of representation theoretic examples, these assumptions always hold. Okay, so an abelian subcategory L in a triangulated category T is called the heart of a T structure. If 2 conditions hold. So we've got a triangulated category, think our triangulated category. We've got an abelian subcategory, think linear complexes. So I didn't really explain this, but these linear complexes are an abelian subcategory inside this triangulated category. So that's what you should think, but if you have an abelian subcategory of a triangulated category, it's the heart of a bounded T structure if 2 conditions hold. So the first condition is that if you take objects in this abelian subcategory and you shift them, there are no HOMs from more positive shifts to less positive shifts, which we sort of saw here. There's no, the top half, there are no HOMs from objects in the top half to the bottom half. That's one condition. And the second condition is that all objects in the category can be filtered, so the subquotients are shifts of guys in the abelian category. So more formally, the statement is that every object fits into a sequence of exact triangles where these guys are in shifts of L, but what you should think, because that's really what's going on in our example, is these E's are all chain complexes, these are subcomplexes, these E's are subcomplexes, and the subquotients are all shifts of linear complexes. So that's this part B is just the picture up here, the boxes. You've taken an arbitrary complex, which is not linear, and you've sliced it into linear complexes. Okay. So that's what a T structure is. And now if you have a group acting on your triangulated category, so for example, the braid group. Yes?
How can I see that this is a linear complex if I don't know what an internal gradient is?
Again, so that's a good question. So when I draw this guy horizontally, I just mean that these guys are in the same level. Now, in this zigzag algebra case, there's essentially no ambiguity. I mean, if this map is non-zero, the only possible shift that could go here so that there is a non-zero map is -1. The Hom space, I mean, the Hom spaces in this category are so small that you can never write down gradings and just ask yourself which morphisms are non-zero, and that kind of completely determines the possible gradings. Yeah, I mean that's a fair question. Yes.
Can you remind me, what is the relation between linear and minimal?
Okay, so yeah, good question. So we're working in the homotopy category of complexes. So sometimes you'll have two objects which are isomorphic in the homotopy category, but not isomorphic as chain complexes. So minimal complex is a completely general thing. It's not about the T structure. Minimal complex just means if you look at, so you fix an object in your category, you look at its isomorphism class in the homotopy category. That could consist of many different chain complexes. The minimal one is the smallest chain complex in the isomorphism class in the homotopy category. So you've applied homotopies to make it the thing as small as possible. So that's minimal. Linear, an object is a complex is linear if its minimal complex is linear, meaning in the minimal complex, the internal gradings and homological degrees match. Yeah. So somehow the nice thing here, which I think really is not true in general triangulated categories, is in this particular triangulated category, you can talk about chain complexes and chain maps and just work with minimal complexes and just do kind of simpler, like thinking about subcomplexes, quotient complexes, things like that. Okay. So the braid group acts on T. So another set on which the braid group acts that we might think about is the braid group acts on T structures. Because if I have the heart of a bounded T structure, that's an abelian subcategory of my category, and I have an autoequivalence, I can just act. And I get a new abelian subcategory of my triangulated category, which is the heart of a new T structure. So the set of T structures is some sort of space well, it's a set that one might want to study. And you might, informally try to think about, you might want to think about this as like trying to think about some sort of Grassmannian in a vector space. You want subspaces of a vector space. So T structures and abelian subcategories in a triangulated category are a sort of Grassmannian-like object you might want to study. Apparently, it's hard to say much about a group from the action on T structures. And part of the reason is that T structures are kind of discrete. This is a set, but we would want some way to maybe make it into a topological space or fatten it up into a simplicial complex or something. That's, well, there are ways one can try to do that, but they're not all that easy to study. So it's appealing to try to study the braid group action on T structures, but somewhat difficult to do. Okay. So, so where we're headed with this is, so in a moment I'm going to tell you what in 10 minutes or so I'll tell you what a Bridgeland stability condition is. A stability condition on a triangulated category is a refinement of the notion of a T structure. We're going to take the notion of a T structure and we're going to refine it a little bit in such a way that the moduli space of stability conditions is an interesting topological space. In particular, it'll be a complex manifold. So here we just have a kind of discrete set of points. We're going to refine this notion in such a way that the moduli space of stability conditions is a complex manifold. And so instead of having a group action on just this set, we'll have a group action on a complex manifold. Okay. But in order to tell you that definition, we need to have a brief aside. So this is stability functions on abelian categories. Okay. So for a couple minutes, we're going to leave the world of triangulated categories and just think about abelian categories. Okay. So let me get a definition. A stability function on an abelian category, which I'll call L, because the one that we'll start thinking about in a moment is linear complexes. A stability function on an abelian category L is a group homomorphism, typically denoted Z, from the Grothendieck group of L to the complex numbers, such that if I take any object in L, the class of that object lies in what I'll call H, which is the strict upper half plane. So H here is, so here's the complex plane. H is, here's the origin. H is all of this. So it's the it's the upper half plane together with the negative x-axis. Okay, so this is the upper. Okay, so that's what a stability function is. So how do you get? So this guy is called a central charge. So if your abelian category has finitely many simple objects, so if, let's say, P1 through Pk are the simple objects of L, so that the Grothendieck group of L is just the free abelian group spanned by the classes of the Pi, then it's very easy to think about what a central charge is. What do you need to do to specify a central charge? So Z, the central charge, is of course determined uniquely by a choice of a vector in H for each Pi. Right? So if you want to get a central charge on an abelian category, well, you need a group homomorphism. Well, that group homomorphism is determined, it's a free abelian group, so it's determined by where it sends a basis. And the only condition is that each basis element had to go to the strict upper half plane. So So let me just give you a bit of a running examples just to work with these things. So we'll maybe have 2 examples here. So let's say our simple objects are, let's say that the simple objects are, let's say we have 2 simples, let's call them P1 and P2 for a second. Then here's the origin. One central charge might send the class of P1 here and the class of P2 here. And another central charge might send the class of P2 here and the class of P1 here. This would be perfectly reasonable. This completely specifies a central charge because to extend to homomorphism, I just extend linearly. Okay, now what so what do you do with, what does one do with central charges? Well, if you have a central charge on an abelian category, it allows you to define stable and semi-stable objects. So I'll tell you that definition. Okay. Now, if you have a central charge, the central charge of a stability function, then you can define, it determines a collection of objects in the abelian category called the stable objects or the semi-stable objects. So, and to do that, then, so we denote by, for any object x, phi of x, the phase of x, which is just, so x is an object, its class is some vector in the upper half plane under the central charge, and the angle that vector makes with the positive real line is the phase of the object x. So this phase will be, we scale the phase so that this is 0 and 1 is over here. Okay? Yes?
So it's can you explain the terminology central charge, or
No. It's a good question. Does anyone know?
No, I think it's the central charge of supersymmetric field theories, not the two-dimensional CFT central charge, but concept from supersymmetric field theories. So it measures the charge of UPS-lab objects.
Yeah, I mean, so so stability in abelian categories, which I'm talking about here, predates stability in triangulated categories. It goes back to the study of vector bundles in algebraic geometry, and there I don't think the word central charge is used at all. But yeah, that's right. So maybe I should not ever, so when we're talking about stability for abelian categories, it might be a bad idea to use the word central charge. I don't know. I mean, that's not, certainly if you're talking to algebraic geometers who think about stability conditions in algebraic geometry on categories of coherent sheaves, they might not ever say central charge. But once you're working in triangulated categories, you say it, and it's from physics in some sense, yeah. Okay, so this is the phase. So now definition, X in L is semi-stable if for all proper sub-objects of X, the phase of the class of Y is less than the phase of the class of X. So this notion of sub-object requires being in an abelian category to talk about it. So what's the picture here? You have, the picture here is you have an object X. So you look at its class in the Grothendieck group. Under the central charge, that's some vector. The class of X is here. You look at all the sub-objects of X. Their classes are some other vectors in the central charge, and you see where they lie. The object X is so stable when this holds, semi-stable if we weaken it to less than or equal to. So the object X is stable if for all the sub-objects, the value of the central charge on those sub-objects lives here. Okay? And otherwise, the object is not semi-stable. So we say semi-stable of phase of whatever its phase is. Okay. So now so what is important here, and this is one of the reasons why this is introduced. So now any object in the abelian category has what's known as a Harder-Narasimhan filtration. This is the upshot of having fixed the central charge and being able to talk about semi-stable objects. So every object X can be filtered such that the subquotients are all semi-stable with decreasing phase. So all the yi are semi-stable, and the phases decrease. Okay, and this filtration is canonical. This once we've chosen a central charge, this filtration is unique. Unlike, for instance, if you're talking about Jordan-Holder filtrations in an abelian category. If you're talking about Jordan-Holder filtrations in an abelian category, those are typically not unique. They're unique possibly up to some permutation. This choice of central charge, which is really a choice, rigidifies that so that you get a canonical filtration of each object. And this is useful if you want to start constructing moduli spaces of objects. You'll get much nicer spaces if you study moduli spaces of stable or semi-stable objects. And that's why this notion is important in geometric invariant theory for that reason. Okay. Now, so bear with me. We're almost going to get back to braid groups. So let's make one more observation. So again, L here is an abelian, So what is the moduli space of stability functions on L? Let's say L is abelian with, say, n simple objects. Then the moduli space, what's the parameter space of stability functions on L is what? Well, a stability function is completely determined by a vector in H for the class of each simple. So this moduli space is just H to the n. The space of stability functions is parameterized by H to the n, which is basically a complex manifold. It's not quite a manifold because of this, because you could have stability functions which have some values here. So if you had a point here, it's only going to have a half-open neighborhood. So this is almost, but not quite. It's a manifold with corners, basically. Okay. All right. Yes.
Is there a reason for adding in the negative x-axis here?
Yeah, you'll see in a second. But, at least from the point of view of triangulated categories, there is. Okay, so now back to triangulated categories. So you should see something, hopefully you recognize something similar here in the Harder-Nahr-Simon filtration in abelian category. This said every object can be filtered so the subquotients are semi-stable. That's kind of like a T-structure in a triangulated category. What did a T-structure in a triangulated category say? It said every object can be filtered so the subquotients lie in shifts of the heart. So if you have a triangulated category and you fix a T-structure, so here's our triangulated category. If we fix a T-structure, then every object here can be filtered so the subquotients are in shifts of the heart. If now we put a stability function on the heart, we can further filter all the objects that are in shifts of the heart so that the subquotients are semi-stable. Okay? That's what a stability condition on a triangulated category is. It's a T-structure together with a stability function on the heart. Okay? So the definition, a stability condition on a triangulated category T is a T-structure, a bounded T-structure, whatever, together with a stability function on the heart. I'll write that in another way in a moment. So there are two important points to note here. So if we fix a stability condition on T, then this is one of the important points, then every object in T has a Harder-Nahr-Simon filtration. It gets sliced up according to the T-structure, and the slices of the T-structure themselves get filtered by the stability function. So, in other words, so E fits into a bunch of exact triangles like this, such that all the FIs are shifts of semi-stable objects of the heart. Okay. So I'll try to do some examples and explain this a little bit more completely, but just so as not to miss the punchline, let me restate a theorem, a couple theorems. So any questions about so so one point to keep in mind is that the value of these stability conditions is that they give you a canonical filtration of every object in your category. Of course, you had to make some choices in order to get that filtration, but after you make those choices, there's no other choice to be made. Okay. So to get a stability condition on T is a T structure and a stability function on the heart. These stability functions on the heart, are parameterized by this complex manifold with corners. So what Bridgeland proves is that actually these spaces here, so they glue together nicely. If you take different T structures, so if you fix a T structure, then the space of stability conditions on T with that chosen T structure is just a copy of this kind of cell. So you could choose a different T structure, like you could take the original T structure and you could tilt it. That's a new T structure. And you could look at stability conditions on that T structure. That's another copy of this space. And the point of this half-open interval is that they glue up nicely. So Bridgeland proves that the moduli space of stability conditions on T is a complex manifold without corners of dimension the rank of the growth and group. So here we have finite rank growth and group. So let's let stab T that's more original statement. Moreover, so so I'll come back to the so a stability condition on T is usually denoted by a pair like this. So this set P tells you what the semi-stable objects in the heart are. And so the semi-stable objects in the category are the shifts of the semi-stable objects in the heart. And then this is the central charge. So if you have a stability condition, so a stability condition, let's call it sigma, there's a map to the space of central charges that just forgets what the semi-stable objects are and just remembers the central charge. Okay? So this is a complex vector space, and the central charge lives somewhere in this complex vector space. So this map pi. The map pi from stability conditions to central charges is a local homeomorphism onto its image. Yes?
We may have addressed this already, but how does the stability condition on the heart extend to the stability condition on T?
How does a stability condition on the heart extend to a stability condition on?
The big triangle.
I mean, the way I defined stability condition was it's just a T structure together with a stability condition on the heart. You could phrase it without specifying a T structure, but.
But this Z is supposed to be a stability condition on big T, right? Or is that?
I mean, a point here is a pair.
Sorry, am I confused? Is this a straight T that's supposed to be the heart? No, in the theorem. The target of the theorem.
Oh, here?
Yeah.
Oh, I mean, same thing as, same thing, growth in the group of the heart, which is the same as the growth in the group of T. Yeah, I mean, yeah. Yeah, that's a good point. Yeah.
You should say the phase of a shifted object.
Yeah, that's right. So if you take, if X in the heart is stable of phase phi, we say that a shift of X is stable of phase P plus K. Okay.
And then in interpretation, actually
Yeah, that's right. This the Harder-Nahr-Simon side, yeah, that's right. I meant to write that here. shifts of semi-objects in L, and with this definition of phase, in the Harder Nahr-Simon object filtration of any object, the phases are decreasing. Yeah, good point. Yeah, thank you. Yes?
And what is the first part of the theorem? So, I mean, you didn't tell us how to. So is it part of the theorem that you can do things nicely, or is the theorem saying, okay, so there is a natural way to do, and this gives actually you money for it?
So actually what Bridgeland does is he defines a metric on the space of stability conditions directly and proves that the induced topology gives the space the structure of a complex manifold. But that metric is, this space here has an obvious structure of a complex manifold, and that is if you look at this subpart of the space of stability conditions, the topology he defines agrees with this topology. So everything is essentially inherited from the topology of this complex vector space. That's the fundamental complex manifold that is determining the topology. Uh-huh.
What do you mean by phi plus k? Not one.
If x has phase phi, if x was in the heart, that phase was some real number in the interval between 0 and 1. Now I take a shift of x. That's no longer in the heart. It's in the shift of a heart. But I want to call this guy a semi-stable object of the triangulated category, and I want to assign it a phase. This is the phase that we assign it. So this is some real number. Okay. Okay. Okay, so now let me just rewrite what this statement actually says in the case, what's actually true in the particular triangulated category that we've been studying, which has a braid group action. Okay. Okay, now. T is now the homotopy category of graded projective zigzag modules. And now so we had this map from stab T to now here the relevant thing for this example is to forget the Q's. So we set Q equal -1 in the growth unique group, because I just want a free abelian group. And we have this map pi. And this is this local homeomorphism from Bridgeland. Now, in this is just the root lattice of the Weil group. So this is the space, in the first lecture when we were talking about Weil group actions, this is the space on which the Weil group was acting when we were studying that Weil group action. Okay? So, theorem. So this is, so not written in exactly this language, but basically, so Richard Thomas wrote about this in type A. Bridgeland wrote about it in type ADE and maybe affine type ADE. And Licata wrote about this in the language of the pre-projective algebra of simply laced Kac-Moody type. And so you can translate all of that over to this, this setup. Is that, so let me first state it in type ADE, and then I'll state it more generally. So the image of pi this map here is, so let me call this whole space, this was the space V that we were talking about in the first lecture. I denoted this by V. Where here H alpha is Z such that Z of alpha equals 0. So, in the space of all possible HOMs here, which ones are central charges of stability conditions? The ones which are central charges of stability conditions are all of them except you have to remove some hyperplanes. Okay? So the central charges which vanish on a root are precisely the things which are not in the image of this map. Okay? So in the okay. And let me just say out loud, I won't write it down right now, but if you're not in type ADE, if you're in more general Kac-Moody type, then the theorem is essentially the same, except you have to remove a little bit more. You have to also remove the imaginary cone from V. So after appropriately defining X reg, I might have written that down in the first lecture, I don't remember, but then the statement holds more generally. But to understand the statement, you have to say what the imaginary roots are, and I don't want to do that right now. Okay. So moreover, this is maybe continuing this theorem. The map pi from stab T to X reg on W is a covering map. So we have this local homeomorphism here. The image is exactly this space. The Weil group acts on this space. So you get a map to this mod W, just the mapping to the W orbit. And this map is a covering map. Okay? Now, in this, so what's the... Yeah, so actually, once you define X reg, this is true in non-ADE as well. That's basically follows from Licata's work on pre-projective algebras. Yeah. So the only reason, it's just outside of ADE, you have to take out a little bit more here to describe the image. But the map to X reg, so there, in non-ADE, you also have to take out a bunch of other hyperplanes, any hyperplane in the convex cone of the positive imaginary roots. So you take out the hyperplanes for positive imaginary roots as well, and then the statement is true. Yeah, that's right. Now, so now in the last 5 minutes, let me what I think is the punchline. So from this, it follows that the braid group appears twice in relation to the space stab T. How? Well, let's think about groups acting on the moduli space of stability conditions. Forgetting anything about the specifics of this image, there's an obvious group which acts on the moduli space of stability conditions, namely the autoequivalence group of the triangulated category. So if F is in autoequivalence, And this is a stability condition. Then you can define a new stability condition just by acting on the collection of semi-stable objects, transporting them by F, and by acting on the central charge. Where, just to be so this Z was a homomorphism from the Grothendieck group to C. Here's a new homomorphism from the Grothendieck group to C. Okay? Sorry, this bracket should have been out. So the autoequivalence group of T just acts on the space of stability conditions for free. But in this particular case, now let's look at the so in particular in our case, the braid group acts on stab T because we have the action of the braid group on T by autoequivalences. So that's one appearance of the braid group in relation to stab T. But now there's a theorem of this is van der Leck's thesis, which is that pi 1 of x reg mod W is the braid group. If you're outside of ADE, it's there's also a braid group across integers, but let's not worry about that. So pi 1 of x reg mod W is the braid group. So now, since stab T is some covering space of x reg mod W, you get an action of the braid group by deck transformations here. Okay? So the linear action of braid group on T gives rise to an action of the braid group on stab T. And there's also an action by deck transformations. And so now theorem, this is written up carefully in type A by Thomas, but the same argument, he gives goes over more generally, is that these two actions of the braid group agree. Okay? So now, in the last minute, I'll tell you what what is the most important question in the abstract theory of braid groups? The biggest open problem, if you're a group theorist interested in these groups, is the K pi 1 conjecture, which, by virtue of this, can be restated as follows. The space stab T for our T is contractible. So every open problem about braid groups that I'm aware of will follow if you can show that the moduli space of stability conditions is contractible. The way the K-pi-1 conjecture is usually phrased is that usually one constructs some other model for the universal cover of this space and conjectures that it's contractible. In particular, the conjecture has two parts, really. It says, first of all, this covering space is the universal cover. That statement is equivalent to the faithfulness of the braid group action. And moreover, that space is contractible. Now, so I'll take 30 more seconds. So my opinion is that, and this is an opinion that is not yet justified by theorems, so take it with a big grain of salt. But my opinion is that this restatement of the K-pi-1 conjecture is significant in the sense that there are many, many, many new tools that you have to study this space that were not obviously available to you in previous formulations of the K-pi-1 conjecture. In particular, one of the things you want to understand in the K-pi-1 conjecture is the action of pi1 of this space on its universal cover is a very important part of that. That action is not really a linear object. It's not really amenable to tools of linear algebra. But that action is the same as this action, which is very much a linear object and which can be studied using lots of tools of homological algebra. Now there are serious group theorists who think about the K-pi-1 conjecture and make a lot of progress in partial cases. As far as I can tell, none of the papers that make real progress on this paper talk about triangulated categories or actions of groups on categories or something. So this is an example of what will hopefully be a bigger story relating questions in geometric group theory to questions in representation theory of the form groups acting on triangulated categories. Okay, so there's a lot more to say, but I'll stop there.